Here we go with the second of the scripts for week 11 of Math 156, this one on one-sided confidence intervals. The first example is, as is often the case, straight from the textbook. If you haven't studied example 7.14 in the textbook, stop and read that now and then come back. Welcome back. So you know all about this lake water. The average lead level based on 15 samples is 7, and the standard deviation estimated from these samples is 2. And what we want to do is get a one-sided confidence interval where we can say we're 95% confident that the true level of lead in this lake water is at least such and such, presumably, and therefore you'd better not drink it. So, if we're going to work with the student t-distribution, we need a standard error. We divide the sample standard deviation by the square root of the sample size to get that, and we assume that the data have a t-distribution with 15 minus 1, or 14 degrees of freedom, and we get the 95% quantile for that t-distribution. All we have to do now is multiply that quantile by the standard error, subtract from the sample mean, and we have a number that has the desired property, namely that the probability that the true mean is greater than that number is 95%. Well, that was easy enough. Now let's do a simulation to see how this works out in a case where we actually know the population distribution. So we're going to assume that the distribution of lead in samples from this water is normally distributed with a mean of 7, a standard deviation of 2. Crank out a single sample, get the sample mean, the sample standard deviation, divide by the square root of 15 to get the standard error, get that student quantile, which comes out the same every time, and compute x bar, which is a random variable, minus the 95% quantile times the standard error, another random variable. So this is a random variable. It came out 4.999, but just to convince you, it really is a random variable. I'll run those lines again. This time it came out 6.45. What's the property of this number? Well, 95% of the time it's going to come out to be less than 7. So let's have a look at the t-distribution we're assuming. There's a plot of it, and I've shown with a red vertical line our actual sample. If I do that again, the red line shows up in a different place. Okay, now we'll run 1,000 simulations. I'll set up a blank plot, extract a sample, get the statistics from that sample. I'm foolishly recomputing this quantile 1,000 times, but it doesn't take that long. Compute the lower limit for our one-sided confidence interval, and if that comes out to be less than 7, then our mean was greater than L, and we were correct. Let's count how often that happens. And at least the first 100 times, let's plot some line segments so we can look at what's going on. So here's the result of the first 100 of those 1,000 simulations. The horizontal lines are the confidence intervals. The sample mean is shown in red, and you can see that every time we have subtracted something from that based on the observed standard deviation to get the lower limit. If we put the true value, which we know because we're doing a simulation with a mean of 7, on there in blue, you notice that most of the time the blue line cuts the confidence interval, but we computed this on the assumption that 5% of the time it wouldn't, and sure enough, 94.2% of the time our confidence interval included the true mean. Now this next topic is tricky. Not only should you stop the video and go back and look at example 7.16, you should also go back to the math notes and read up on scale parameters. Welcome back. You've done that right, and you remember that if you have a normal distribution where the mean and standard deviation are proportional to one another, then the ratio of the sample mean to the true mean, the one and only parameter of this distribution, is a scale parameter. It will, of course, have a mean of 1, and it will have a standard deviation, in our example, of 2/7. So we're taking a different model now. We're saying with this lake water, the concentration of lead is normally distributed, and the standard deviation is 2/7 as large as the mean. Let's extract a sample, compute the usual statistics, and if we rescale everything by dividing by 7, of course, that's not going to change the number that we are assuming satisfies a student t-distribution. So we want the same old quantile, the 95% quantile for 14 degrees of freedom. And since we're now assuming not a normal distribution but a student t-distribution with a mean of 1, we take 1 and add on the standard error to get a quantity that we will call u. And then, in order to get the lower limit of the confidence interval, we divide by u. The argument here is when we draw samples from this distribution, every once in a while we will get something that's considerably larger than the correct ratio of the sample to mu, namely 1, and we divide by that upper limit to get something that'll be less than the true mean of 7 95% of the time. Now this has one big advantage over the previous approach. In the previous approach, we computed the lower end of the confidence interval by subtraction, and we could in principle have made stupid statements like, we're 95% confident that the actual concentration of lead in this lake is greater than -3. Of course, it has to be positive. With this approach, we're taking into account the fact that the data are necessarily positive. Now let's run some simulations to see how this works. This is a repeat of the code I just ran in the subtractive case, except that I have computed my lower end for the confidence interval by the new approach. And we might as well display the results from the old approach as well. Okay, now have a look at this. The bars that are shown are the confidence intervals based on the scale parameter approach. The green bars on the plot are what we would have got from the subtractive approach. So we have computed a somewhat different confidence interval in this approach. There is the true mean, and again, roughly 95% of the time, the true mean was captured within our one-sided confidence interval. One last example. North Carolina babies again. Read in the data, extract the weights as a vector, and look at how many babies we've got, 1,009 of them. In this case, the sample size is so large that there's no point in distinguishing between the student t-distribution and the normal distribution. If you look at the quantiles for the two distributions, they agree to 3 decimal places. So we take the 95th quantile times the standard error. That gives us a lower bound. We can do it with student t. We can do it with normal. And it doesn't really make much difference which we do. Needless to say, this test has also been automated. If you use t.test with alt equals greater, it will give you a one-sided confidence interval, and it gives, I believe, exactly the same number that I got from the t-test, 3422.98. Yes, 3422.98. And that ends this video.